Welcome to this webinar. I'm going to talk about failure rate classification, safe or dangerous, and specifically focusing on how we need to use fail low and fail high failures. And then we will get some certificates sometimes with fail high and fail low failures listed. And what do they mean? They're not safe and dangerous. So that's what we're going to talk about today. Why do we have fail low and fail high failures? And how do we convert them to safe and dangerous? But before we start with that, let me wish everybody a Happy New Year. I hope that yours is healthy, happy, and of course functionally safe. Best wishes to you and yours. My name is Iwan van Buren, and I'm here at exSILentia in Sellersville, Pennsylvania. It's our U.S. headquarters. I'm the Director of Product Development, and in addition to that, I assist manufacturers as part of our certification activities. I help end users with regard to the implementation of the ISA 84 or IEC 61511 functional safety standards, and I'm responsible for the development and maintenance of our exSILentia software and our SILstat live event recording software. Today, we're going to talk about a 4 to 20 milliamp output signal on an analog transmitter. That's basically the main content of this webinar and how that applies to functional safety. We're going to look at the analog transmitter failure modes. We're going to talk about the application of that transmitter and the impact on the failure mode classification. And then we're going to look at how we can very easily do this classification of failure modes in our exSILentia software. So let's start with a 4 to 20 milliamp output analog transmitter. To be a little bit more precise, I'm going to talk about a microprocessor-based version of that. And if you just Google on the internet for transmitters, analog transmitters, you may find a picture, as you see in the upper right-hand corner here, of what a typical transmitter may look like in the process industry. Schematically, there tends to be a sensing element or a metering body that sends a signal to a microprocessor, and that then drives a 4 to 20 milliamp output signal. So very schematically, there's three parts to a transmitter, a little bit more detailed in the picture below as we sometimes perform failure mode effect and diagnostic analyses on these. Obviously, we go into a lot more detail, but there could be a D to A circuit to convert the microprocessor signal to from a digital to an analog signal and so on. Let me get here. So what does the 4 to 20 milliamp output signal usually look like? Well, typically our processes are dynamic, so we can see a squiggly line, as you can see here on the slide, that follows the process value as it changes over time. And our normal process signal in a 4 to 20 milliamp output circuit will be between 4 milliamps and 20 milliamps. And any signal in that range is typically considered a healthy transmitter signal. Any signal outside of that range, either under range or over range, is usually flagged as an unhealthy transmitter signal. Those are not valid process points. So that's the basis of the analog transmitter as we're going to talk about it today. So let's look at typical failure modes that we will see as a result of a detailed analysis of these transmitters, for example, performed using a failure mode effect and diagnostic analysis. One of the failure modes that we come across is a frozen output. Basically, the output is stuck at, for example, 20 milliamps, and regardless of the process measurement, that output will not change. that output is stuck in the normal operating range, in what we consider the healthy range of the transmitter signal. It is presumed correct, so we will not be able to detect this as an unhealthy transmitter signal. Since we are no longer able to follow the process variable, since we're no longer able to give the actual information of the value in the process, it's a dangerous failure. We can no longer indicate that we need to transition to the safe state. We can no longer go through a trip point. We're stuck. So these frozen outputs are very easily classified as dangerous undetected. So on a failure mode effect and diagnostic analysis report, you typically don't see a failure mode of fail frozen. You typically see a fail dangerous undetected failure mode, because these failures are dangerous undetected. And an example could be an output bit on the microprocessor being stuck. Doesn't matter what the sensing element does, the output will always, always be frozen on let's say the 12 milliamp. Another example of a transmitter failure could be an output going over range. So for whatever reason, something goes wrong in the transmitter, a component fails, and the output jumps from somewhere in the in the healthy operating range to out of range. We get a stuck output. And again, regardless of the process measurement, that output will not change. It will just be simply higher than the 20 milliamps. That fault in this case is not detected internal to the transmitter. It's just a fault that will drive that output over range. We call these failures fail high. Are they safe or dangerous? Well, we'll see that we don't really know that until we know how the transmitter is applied. Yes, it's unhealthy, but the question is, can the logic solver detect this out of range signal? So on the application level, we don't really know if this is a detected or undetected failure. On the application level, we don't know if this is a safe or dangerous failure until we are actually familiar with the application. So when we do the failure mode effect and diagnostic analysis, we classify these failures as fail high. Similarly, there are some failures that will drive the output under range. For whatever reason, let's say a resistor in the output circuit fails open. Now your output will go to 0 milliamps. Doesn't matter what the process value does, your output will no longer change. You drop to 0 milliamps, below 4 milliamps. The failure, the failure is not detected by the transmitter. It just, the output goes to 0, and we classify those as fail low. And it's the same story as for those fail high failures or overrange failures. We don't really know if this is a safe or dangerous failure. We don't really know if the logic solver will detect this. So that's why we classify them as fail low. Then we have failures that will be driven to a predefined fault point. So your modern transmitters have a switch or a jumper setting that will indicate if you want to drive outputs to a low value or a high value based upon an internal detected failure. And those values could be 3.6 milliamps and 21 milliamps outside of the normal operating range, but predefined specific fault points in the 4 to 20 milliamp signal. We call those failures detected. They're detected internal to the transmitter, and they're specifically driven to these levels. So let's say I pick a low range, drive it low to 3.6 milliamps, then a failure that is detected by the transmitter will be driven to that 3.6 milliamp. So it's detected internal to the transmitter. Is it safe or dangerous? That depends on the application. Obviously, it's an unhealthy signal. It's outside of the 4 to 20 milliamp range, but does the logic solver detect it? We don't know. It depends on the logic solver. We'll see that in the next section. So these detected failures can either go over range or under range based on that setting. And then finally, we may have failure modes that simply have no impact or no effect on the transmitter's output to perform or to communicate a particular process value. But maybe the occurrence of that failure may result into a noisy signal. So that's what I try to represent with the dotted line, a more choppy, noisy signal. But as long as it's within the safety accuracy of the transmitter, the transmitter can still indicate, hey, that process value goes up, and it can still follow, and it can still result into a trip in case of a high trip. We classify those failures as residual or no effect failures. They basically have no impact on the transmitter capability to perform the safety function. The signal is just not a nice line anymore. It's choppy. I got a screenshot from our third edition of the Safety Equipment Reliability Handbook for a generic DP pressure transmitter. Obviously, you probably know that we've released the fourth edition by now, but I just wanted to get a data sheet, and I didn't want to favor any manufacturer with example data as you can see it for a transmitter. And what we can see on this data sheet is that there's a fail low failure rate of 400 fits, a fail high failure rate of 150 fits, a fail detected failure rate of 150 fits, and a dangerous undetected failure of 600 fits. So that's the fail frozen, basically, and then a fail residual of 200 fits. So that's information that we may get from a failure mode effect and diagnostic analysis for a particular transmitter. So if that's the data, the question is, how do we classify this as safe or dangerous? Because we need to use this in our SIL verifications, and in our SIL verifications, we don't really talk about high and low. We talk about safe and dangerous. So we need to look at how these failure modes are implemented, and how the transmitter is implemented, and then how the failure modes are transitioned into the appropriate categories. So first, all right, let's look at the 5 failure modes that we identified. A frozen output. I already said those are very clear. The dangers undetected. We don't really have to talk about those anymore. The no effect failures, yeah, they have no impact on the capability of the transmitter to perform its intended function. So they're not safe, they're not dangerous, there's simply no effect on the transmitter. So the failure modes that we really need to look at are the fail high, the fail low, and the fail detected failure modes. So let's do that. Let's start with fail high. Well, let's say I have a high trip point. If I have a high trip point, a fail high failure will go through the trip point and therefore indicate a transition to the safe state. After all, the process value is greater than the trip value. So in case of a high trip application, that fail high failure is safe. Well, what if I have a low trip application? Well, in case of a low trip application, that fail high failure will go away from the trip point. It will not initiate a trip. It will actually prevent the transmitter from initiating a trip because it's stuck in that overrange. So that is a dangerous failure. It can no longer perform its intended function. And in contrast to the high trip where it will initiate the trip. So here's an example that the actual application of the transmitter will impact how you classify a fail high failure, either as safe in a high trip case or dangerous in a low trip case. Well, let's look at fail lows. And it shouldn't be a surprise that this is pretty much the same except the opposite. Now, if we have a high trip scenario, the fail low failure will go away from the trip point. It will no longer, the transmitter will no longer be able to indicate a dangerous process condition. It's not initiating a trip, therefore it's dangerous. In a low trip application, the fail-low failure will actually go through the trip point, indicating that the process value is beyond the trip point and initiate a transition to the safe state. So low trip, fail low is safe. High trip, fail low is dangerous. So it's the opposite of the fail highs, but we can clearly see that how we implement that transmitter will impact how we need to classify the failures. And that's why the FMEDA provides you fail high and fail low failures, because at the point that the FMEDA is done, we don't know if you're applying it to a high trip application or a low trip application. All right. The next parameter that we need to consider is actually within the transmitter itself. Your transmitters can be configured to either drive the output to a predefined overrange state or a predefined underrange state in case of an internal detected failure. And the Namur standard, Namur 43, actually addresses the 4 to 20 milliamp range with the predefined fault ranges. And it talks about a 3.6 milliamp range and a 21 milliamp range, as you can see right here, as the predefined fault ranges. Some manufacturers have a default setting of 3.75 milliamps because a hard signal, the HART signal, will not work at 3.6 milliamp. It will work at 3.75 milliamps. So there may be a different predefined fault range for some transmitters, or you may be able to specify different ranges based on the transmitter that you purchase. Some manufacturers go to 21.5 milliamps on the overrange. So it's something to take note of when you purchase a particular transmitter or when you use a particular transmitter, what the actual ranges are, because they're important in your programming later on. But what we can see here is that if we set that jumper to, let's say, overrange, then my failed detected failures will be driven to, let's say, 21 milliamps. So it will behave similar as a fail high failure. If that jumper or switch is set to drive it under range or low, those failed detected failures that we talked about earlier will behave the same as fail low failures. So the actual configuration of the transmitter impacts how the failure rates for that transmitter are classified. All right, now we talk about the healthy operating range. And we say that any signal between the 4 to 20 milliamp range is considered healthy. Well, that all sounds very nice, but can your logic solver actually detect an out-of-range signal? And most people say, well, modern PLCs, yeah, they detect an out-of-range signal. They can easily flag if a transmitter is unhealthy. And that's true. And obviously, when you detect a fault like that, you need to do something with it. So you need to either enunciate or consider it as a trip. We'll talk about that in a little bit. But we need to be very careful when we say, yeah, our PLCs can detect these unhealthy transmitter signals. Because what I've seen in some cases is where we use a transmitter that is compliant to the Namur settings. So let's say 3.6 milliamps is the predefined output range for internal detected failures. But the PLC that it was used with was configured with a 3.2 milliamp unhealthy signal limit. In the attempt to avoid false alarms or false indications of unhealthy transmitter signal, they set it to a default 3.2 milliamp. But that means that any 3.6 milliamp signal would still be considered a healthy transmitter signal in this particular implementation of that PLC. So we need to make sure that when we use these transmitters that have the capability of enunciation diagnostics, that we that we can actually use that information, that we can actually benefit from that information provided. So we need to make sure that we understand what the fault ranges are of the transmitter, and when we implement it in the logic solver, we need to make sure that the logic solver will actually see it as an unhealthy transmitter signal. Some end users like to implement or have the ability to implement trip delays. So we had the earlier example of a fail-high failure, where a fail-high failure will go through the trip point in a high trip case and will be considered safe because it will be initiating a trip. Process value is greater than trip value. If we implement a trip delay, we're basically doing that, or at least for one of the reasons that we're doing that, is to make sure that that transmitter signal is indeed indicating that we really need to trip. Is that value really greater than our high trip point? As you can see, and the transitions are typically very rapid when there's an internal component failure in a transmitter, that output will jump from a normal operating range to outer range very quickly. So even a 1 second trip delay will be able to flag a transmitter signal as unhealthy instead of just in the greater than the trip point range up here. The standard allows that we, instead of going to the safe state at a point like that, that we continue to operate as long as we fix the problem within the assumed repair time. Alternatively, we can say, hey, this is a vote for trip because the transmitter is unhealthy, but the standard allows us to continue to operate. If we decide to continue to operate and not go to the safe state, then again, we have a transmitter whose signal can no longer follow the process value. We know it's an unhealthy transmitter signal. We know it's not a vote for trip. In that case, we would be classifying it as a dangerous failure. So a trip delay, or the input filtering or alarm filtering that we can implement, will impact, again, how we classify failures as safe or dangerous. Then we have different operating philosophies, and I kind of hinted to that already a little bit. In low-demand applications, the standard allows that you continue to operate after a failure is detected, as long as that failure is repaired within the assumed repair time. So if you assume a repair time of 8 hours, you need to fix your problem within those 8 hours, or you need to transition to the safe state. Some companies like to do that. They like to avoid false trips, and they say, you know what, if we cannot rely on this particular safety function, maybe for lower risk hazards, we will continue to operate, and we will fix it, of course, as soon as within the assumed repair time, and maybe we implement some additional risk reduction measures by means of maybe operators spending a specific attention to the variable that is being measured. But if we continue to operate with a failed transmitter, that transmitter is no longer able to indicate the correct process value, it's a dangerous failure. It's detected. We know it's wrong, but it's a dangerous detected failure. If we decide that upon any unhealthy transmitter signal we want to go to the safe state, then obviously we detect the failure, but because of the transition to the safe state, initiating a trip, we would call it a safe detected failure. So this operating philosophy also has an impact, again, on how we classify our failure rates. And to summarize all that, there's this nice table here with pretty much all the combinations. If your PLC can detect outer range signals, yes or no. If you filter out alarms or implement a trip delay, yes or no, on or off. What is your trip point? Is it a high or a low trip point? How do you set your alarms within the transmitter? Drive it under range or over range. And then based on that, failures are either classified as safe, dangerous, detected, or undetected. So that's how we would need to convert those fail high, fail low, and fail detected failures into safe, dangerous, detected, and undetected. Now, enjoy reading the table. enjoy following up on every single scenario to get the correct classification of the failures. As I indicated in the beginning, I'm going to show you how we do this in the exSILentia software, and that will make your life a whole lot easier. Those configuration options that I mentioned, is the trip high, low? Is your alarm setting over range or under range? So do you drive your outputs low or do you drive your outputs high? Can your PLC detect over range, under range signals? Do you have a filter on alarms or do you have a trip delay? Are you consider all unhealthy transmitter signals as a request for trip? Yes or no? Those items that I just mentioned are simple selections in the exSILentia software, and based on that, the failure rates are classified. So if you look at the bottom part of the slide here, the black failure rates are the failure rates that come directly out of the Safety Equipment Reliability Handbook database. The blue failure rates are the failure rates that are classified per our selections, are classified based on our application, based on the implementation of the safety instrument function. And I wanted to show you how that works in the software real quickly, because it is very easy to do. You should see the exSILentia software now, where I have just a simple safety function with a pressure protection function. I've selected the pressure transmitter sensor group. I can collapse the results here and actually also the navigation. We can just focus on the sensor group and the classification of failures. So if I click on this advanced option button, I get this pop-up that will show me all the failure rates. And as you may remember from the screenshot of the data page that I showed earlier, fail low is 400 fits, fail high is 150, fail detected 150, and dangers undetected is 600. That's the data, and 200 for the residual, but we don't use the residual in our calculation because they have no impact on the safety function. So those failures are used as an input, and the blue failures are the ones that are calculated based on the selections. So let's look at the selections. Let's start with a high trip. Let's say I have a high trip scenario, and let's say that my alarms are driven under range. In other words, all internal detected failures are driven to a low under range output, maybe 3.6, maybe 3.75 milliamps. So what does that do for my failure rates? Well, fail high will go through the trip point. Right now I've specified, by the way, I've specified that the PLC detection is off. Right? I don't flag out of range signals as detected. So fail high goes through the trip point, behaves as a safe failure. We're classifying it as undetected because we have the PLC detection currently set off. But you see that the 1.5 for the fail high goes into the safe undetected category. Fail low goes away from the trip point and is therefore dangerous. Again, the detection is off, so it's dangerous undetected. And fail detected, because the transmitter is set to have an underrange output upon detected failures, behaves the same as fail low, so 4 plus 1.5 plus this 6 ends up to be 11.5 in the dangerous undetected category. So now what happens if we drive our outputs over range upon internal detected failures? Well, in that case, what we see is that the fail detected and the fail high both will result in a vote for trip. They both will go through the trip point, and the 1.5 plus 1.5 is now safe. The fail low will go away from the trip point, and they're fail dangerous, undetected. So they're being added to the dangerous undetected failure rate. Let's say I have a low trip. What happens then? Well, a low trip means that the fail low will go through the trip point. Low goes through the trip point, so those 4 are in the safe undetected category. fail high and fail detected, which is currently still being driven over range, are going away from the trip point and are therefore considered dangerous, and therefore are getting added to the dangerous undetected failure rate. And it probably won't be a surprise that if we say, hey, we drive all our outputs under range, that the total failure rate, or that the failure rate classification shows that our outputs are fail low and fail detected 4 plus 1.5 are now safe undetected, and that the fail high is the only one that gets added to the dangerous undetected failures. So with that, we've basically covered how, let me go to that slide real quick, how we classify the fail high failures, either safe or dangerous, the fail low failures, either dangerous or safe, and the dangerous detected failures. The fail detected failures, as a simple selection of failure rates, of operating options. All right. I thought I saw a question, but no, I don't see a question right now. Okay. So let's go back to the tool. So we covered these first two. We covered the first two options. Just trying to get the spotlight. Maybe it doesn't like me right now. Okay. Let's assume we have a high trip and we drive our outputs under range upon the internal detected failure. So in other words, fail high will go through the trip point, fail low will go away from the trip point, and fail detected will behave the same as a fail low. All right. So now, let's say we have our PLC detection on. So what did that mean, PLC detection on? That meant that those outer range signals are now considered detected. All right. What happens to our failure rates? Well, fail high goes through the trip point, is safe, initiates a trip, but those failures are now detected. So they now fall in the safe detected category. If, hold on, I need to erase my line here. All right. If we look at fail low and fail detected, they behave the same because the fail detected failures are driven under range. Both go away from the trip point. Both are dangerous, but they're detected because I detect those outer range signals. So we now see that those failures that were previously added to the dangerous undetected now are added to the dangerous detected failures. So 4 plus 1.5, that's your 5.5 right here. And the 1.5 from fail high goes into the safe detected. I have a question, and I will answer that question in just a bit. So the next step that we can consider is, do we have a trip delay? Yes or no? And if I say, yes, we have a trip delay, so we say the alarm filter is on, basically what we're doing is we're getting a request for trip from the fail high failures, but instead of immediately tripping, we are waiting to make sure that this is a true request for trip, and then we transition to the safe state only if that is a true request for a transition to that safe state. If the failure ends up in the out of range, we know something is wrong with the transmitter, and we can address that. And we can decide to continue to operate, but we basically prevent the spurious failure. So what happens in that case? Well, fail low is still going away from the trip point. Fail detected, going away from a trip point. Both are detected. Fail high is going through the trip point, but we are preventing a spurious failure. We're preventing transition to the safe state by simply saying, hey, something is wrong with the transmitter. We want to flag that as an unhealthy transmitter and continue to operate. So 4 plus 1.5 plus 1.5 is 7. Is now the classification of the failure rates. And finally, based on your operating, so we go back to the slide. Sorry, that's your trip delay accounting. So the previously safe failure is now considered dangerous. Finally, we can say, well, the operating philosophy, we don't want to operate if there's any unhealthy transmitter signal, according to of course, the appropriate voting arrangements. But we don't want to continue to operate if a transmitter in a single non-redundant system it has failed dangerous. We want to transition to the safe state, and we can flag those alarms are voted as trips and set that to yes. And then we will see that all those failures that were earlier in the dangerous detected category are now in the safe detected category. They will cause a spurious failure. We know that something is wrong on application level because we detect them. So we know from a sequence of event perspective what happened and why we tripped, but we're still tripping. And that's, as I said, that's based on the application or operating philosophy of the particular end user, and that's what we're talking about in this last slide. So how fail high, fail low, and fail detected failures are classified depends on how the transmitter is used. Is it a high trip application or a low trip application? Depends on how the transmitter is configured. Do I drive my outputs over range or under range upon a internal detected failure? Then I have, can my PLC or logic solver actually detect over range and under range signals? Yes or no? If it can detect them, can we implement a trip delay or a way to filter out any unhealthy transmitter signals? Yes or no? And then the operating philosophy, do I want to continue to operate if my transmitter failed dangerous, or do I want to transition to the safe state in case there's a hazard that I won't be able to enunciate because my transmitter has failed. So those selections will impact obviously the classification of the failures, and we've seen in the exSILentia software how that is done. We present both the failure rates directly out of the equipment database, as well as the failure rates as they are classified based on the actual use and application of the device. And then the latter, the blue ones, are actually used in the calculation. So my next slide was questions, and there are a couple of questions. The first, what is the difference between fail low and fail detected failures? And that's, I kind of started with that, but let me go back to the earlier slides. What are the typical failure modes of a transmitter? And there are failure modes that will simply result in a frozen output. It's stuck, it doesn't move with the process value, it's in the healthy transmitter signal range. We call them dangerous and undetected. There are failures that will cause the output to go over range. Regardless of what you do with any settings, the output will simply go to an overrange signal greater than 20 milliamps. And we call those fail high failures. There are failures in a transmitter that will drive the output to underrange, and the example will be a resistor failing open in an analog output circuit. All of a sudden you go to 0 milliamps, so you drop below the 4 milliamp output, drop below the 4 milliamp range, you're under range, you're stuck there, you can no longer follow the process value. That's something that we call fail low. And fail detected will be a failure that is detected internal to the transmitter, and the transmitter will drive it either over range or under range based on a jumper setting or switch setting. So those are the fail high, fail low, and fail detected failure modes of a transmitter that we then classify into safe and dangerous, detected or undetected, based on how we actually use that transmitter. So that's, I think that's that question. What is the impact of this classification? Well, I didn't look at that in the tool. I didn't want to. I didn't want this to become a let's look at the probability of failure exercise. But you know, just for fun, let's say that I do not detect any out-of-range signals. Well, you see that all the knowledge that we have in the transmitter, where we drive the outputs to over range or under range, and let's say, that all that knowledge is kind of lost at that point, and you see that the probability of failure on demand is significantly higher than if I say, hey, I can detect those out of range signals. And in this case, based on the failure rates, it's a 2x difference. This is a generic transmitter. If you would play with manufacturer-specific data, you will see that especially the safety certified devices will have more failures that are driven to a particular predefined output. So the fail detected failure mode will be will have a higher failure rate than this example. And you will see at that point that not detecting those internal to the transmitter detected failures, but not detecting them on the application level, will significantly impact your overall probability of failure on demand. You're basically losing all the diagnostics that the manufacturer built in. Another example here is, if I say that I will not vote my alarms as trip, so in other words, any unhealthy transmitter signal we will continue to operate. Well, we see that there's a little change in the probability of failure on demand, but theoretically at that point the spurious trip rate will be equal to 0, or in the meantime to fail spurious will be equal to infinity, because all failures will result into a not trip, because these transitions from a normal operating range to an outer range because of an internal component failure are typically very, very rapid. Will the presentation be available? Absolutely. Everybody that registered will get a link to this webinar, so you can look at this at a later date. What are the residual failures represented in the data is another question here. So the residual failures, are failures of components that are part of the safety critical path, but where the failure mode of that particular component has no impact on the actual output, on the ability of the transmitter to perform the safety function. So an example could be that you have a filter in circuit as part of your output circuit. So you get a nice smooth line, a nice smooth signal, I should say. If that filter fails, one of the resistor could fail, the capacitor could fail in such a way that the functionality of the filter is lost, and your output signal becomes very noisy. That will be a failure mode where very noisy, but it's still, the transmitter is still able to actually move with the change in the process value. That will be a failure that we would then classify as no effect, and then call residual. So residual failures, no effect failures are the same. They're just different words for the same item. We originally called them no effect failures. Then there was a lot of people, including people in the standard committee, that didn't like no effect, and we renamed it to residual. and then the standard introduced the no effect failures. So that's a little bit frustrating on our end, but residual failures are basically no effect failures. Another question, did the alarm filter selection actually change the calculation? Alarm voted as strip will be the only trigger for changing the calc. Actually, the alarm filter does change. And let me show you. If we let's turn it off. So what we have is fail high, detected failures are driven under range, and we detect all out of range signals. And what you will see is that the safe detected failure rate is 1.5 E. I'll make sure that everybody can see the screen. Yes, 1.5 E minus 7. Then if we and the danger detected is 5.5, and you can also see the results are 677 E minus 3 and 766.22 for the mean time to fail spurious. Now, if we say that we do filter those unhealthy signals, we see that those fail high failures are now shown in the dangers detected column. Now, the actual calculation doesn't really change from a PFD perspective. It's still the same 6.77 E minus 3, but that's because we assume that the dangers detected failures are repaired within the repair time, which in this case was specified as 24 hours. Maybe if we make that a little bit longer, that could be an impact, but typically dangers detected failures have a very low impact on the probability of failure on demand, because the time span that they're multiplied with is much smaller than the time span, for example, for the dangers undetected failures, which tends to be the proof test. But you should have noticed that the mean time to fail spurious went from something to infinity, because now we're filtering out all those votes for trips. So if I flip the alarm filter back and forth, you'll see 766 years mean time to fail spurious go to infinity, meaning that all known safe failures, let me rephrase that, all known transmitter failures will be filtered out prior to the signal being used to determine if we need to go to the safe state, yes or no. Let's see, where are the rest of the questions? Oh, there we go. How does fail detected work within the 4 to 20 milliamp? Well, fail detected failures are failures that the transmitter detects. So they're detected within the transmitter, and the transmitter drives the output to a predefined output range, a predefined output point, 3.6 milliamps, 4.2 milliamps, 21.0 milliamps, for example. An example of a fail detected failure could be, and some transmitters use, let's say, something similar as a tuning fork, and if that frequency is off, there's an indication that that one of the measurement items may not work correctly, and they may flag that as a detected failure. So that could be something that the transmitter can detect. Hey, my sensing element gives a value that doesn't make sense, or doesn't give the value at the time that I expected, and the transmitter will then drive the output to that predefined output range. So another question here, and that's actually a good question. Just to clarify, that time delay and alarm filter flag, that only applies if the out of range failures are actually detected. So only if you can detect those out of range signals and flag them as unhealthy, can you, claim that you have an alarm filter capability. So it's not just not just the trip delay that you're implementing. You really need to be able to detect that that signal will end up in the out of range area. So that's a good point here. So if you would implement a time delay, but you have not the ability to detect that out of range signal, then it just simply remains an undetected failure, and you will not be able to flag it as hey, something is wrong with that transmitter. How are the final elements affected with this classification? Not at all. Let me rephrase that a little bit. The classification that we looked at is specific to transmitters. It's specific to analog signals that go into the logic solver. If you look at final elements, then in those cases, there usually is a predefined operating or predefined safety function, where if there would be fail low, fail high type failures, they would already be converted into safe and danger. So we only really see this on the sensor end of the safety function. Another question, I like this one. Do the no effect failures increase the safe failure fraction? Excellent question. And why is it an excellent question? Because the answer is yes and no. So let's look at the yes part. We can see the safe failure fraction here is calculated at 60%. That's because this residual failures are included in the safe failure fraction calculation. If I change one of my parameters up here, consider architecture constraints to IEC 61508-2010, and we go back to the results, we see that the safe failure fraction drops to 53.9%. And the reason for that is that in the definition of a safe failure in IEC 61508-2000, it was stated that any failure that is not dangerous is considered safe. And therefore, by definition, no effect failures needed to be included in the safe failure fraction calculation. IEC 61508-2010 corrected that. No effect failures are identified as a unique class of failures. And that was one of the comments that we as exSILentia submitted to the original version of the standard, that there's more failure modes than just simply safe and dangerous. But the no effect failures are specifically identified in 61508-2010, and therefore they are no longer part of that safe failure fraction calculation. So you will actually see that the safe failure fraction changes for this particular transmitter configuration if I change between 61508-2000 and 61508-2010 edition of the standard. So let's see. A lot of good questions today, guys. I'm very happy with that. All right, there's another selection here that I didn't talk about, and that's in the silver screen here that you may see at the bottom. There is a selection that is called external comparison. External comparison is another selection that we allow you to make in the tool to account for the comparison of two or more transmitters that are measuring the same value. You would expect that if you're measuring the same value with let's say two transmitters, that they are representing the same milliamp outage. And if there is a difference between the two outputs, that could be an indication that there's something wrong with that transmitter. We call it external comparison because it's external to the transmitter. You do it on an application level rather than within the transmitter, rather than the transmitter level. You do it on the application level where you say, hey, they got two measurements, let's compare the values. And you would expect that if there's a frozen output in one, and the other is still moving, that there's a deviation, and between the two results, and then you issue a deviation alarm, and you go out and fix it, or you transition to the safe state. Is there a difference between the analysis, normal analysis and a Moore analysis? No, it's just a predefined output ranges. So 3.6 and 21 milliamps are predefined output ranges that are defined in the Moore document, and had that on the one slide. Let me try and get that up. And I got this picture. I just Googled Namur NE43, and this was one image. And I put the source actually underneath. But that's a picture that I found on Google that demonstrated the ranges. So basically, what this standard says is that 4 to 20 milliamp is the normal operating range. Between 3.8 and 4, and between 20 and 20.8. Are what they call the normal over ranges and under ranges. So that's where your signal may end up a little bit here and there. And then 3.6 and between 3.6 and 3.8, and between 20.8 and 21 are the predefined ranges for indicating that there is a diagnosed failure. Anything beyond that are just simply failures that are not detected by the transmitter. So those are the fail load that goes to 0 milliamps, for example. So I think that was that question. Let's see. So okay, I described, as in my example, I described a noisy output as a no effect failure. Now you really need to understand how the transmitter is being used to make that statement. Noisy, typically, if you look at the safety manual of a certified pressure transmitter or whatever transmitter, temperature transmitter level, you will see a safety accuracy. And what that basically says is that within, and that could be 2%, for example, that within 2%, the output is basically guaranteed. So that means that if, for whatever reason, and maybe that filter fails, and your output deviates by 1%, we don't really consider that a failure from a functional safety perspective. It's assumed that your trip limits are set appropriately according to that safety accuracy. So in that case, it would not have an impact. If you have very narrow trip limits, then a signal that becomes a little bit less accurate could be an issue. That could definitely be an issue. So, for example, if you need to do any measurement with regard to gas flow, and you're using that to control the amount of gas that goes into furnace and prevent overheating, stuff like that. At that point, it becomes a whole lot more important than if you say, hey, on average, I have an output that goes in the, let's say, 20 milliamp range. If it goes above 60 milliamps, I need to go to the safe state, but it hardly ever comes close to 60 milliamps under normal operating conditions. So that's it is that noisy signal is not don't take that as a we can tolerate a lot of noise. You really need to look at the application. I hope that another thing, when we do failure mode effect diagnostic analysis, it is taken into consideration if that has an impact on any future fault. So if in my example, I'm assuming it has no impact on any future faults, but if it would have an impact on a future fault, that would be considered, and then it would no longer be a no effect failure. Another question here is specific on external comparison. Is it within the SIS or external to the SIS and the DCS? Is it automatic or manual? Okay, we're getting to the implementation of some of the functionality here. I would say all standard says all diagnostics need to be implemented automatically in order for them to be credited as automatic diagnostics. So when we talk about external comparison, we are assuming that that is implemented automatically. Does it have to be in the safety and cemented system, or can it be in the DCS? The standard doesn't prescribe that it has to be in the safety and cemented system. However, you need to consider that this is a comparison where you are claiming credit, improvement in safety integrity, that you really want to have under a good management of change. So you want to make sure that the system is not messed with, that the deviation alarms are clear and well enunciated. So we typically suggest to put it in the safety and cemented system, just because that's better controlled. But I can say that the standard absolutely requires that. And I think this is going to be my last question because I'm running out of time. If we have a low failure, but where, let me rephrase it. If we have a failure of a transmitter that will result in a lower value that is not going to the underrange area, how would you deal with that? If my standard signal is 10 milliamps, and for whatever reason I go to 8 milliamps, we would probably classify that as a dangerous failure, because it could also have been that it went from 12 to 10. You remain in the healthy operating range. You're at a stock output. You can no longer follow the process value. So at that point, the conservative approach is to call it a dangerous failure. If you deal with drift failures, then you may drift high, you may drift low. That would probably be the only case where you would ever see a safe failure directly assigned to a transmitter, at least done in an FMEA by accident, because it may drift high, it may drift low. In some cases it goes to dangerous, some cases it goes to safe. But anything that is basically stuck in the healthy operating range, we tend to flag that as a dangerous failure. So I think I've answered all questions. One more here. Does hard diagnostics impact overall calculation? The answer is no, because no hard signal can be communicated to a safety critical. Hard is not considered safety critical. Hard is considered interference free. There's no whenever an analysis is done on a transmitter or even on logic solver, the hard circuitry is typically looked at to make sure it doesn't impact the analog capability of the transmitter. Obviously, yes, you can get information out of it, but we don't take any credit for it in the calculations. So with that, I'd like to thank you for dialing in to this first webinar of 2016. I got some very good questions. I hope it was very interesting to everybody. The webinar will be available or made available to everybody that attended, or I think everybody that signed up. If you have any further questions, feel free to reach out to info@exida.com, and we will see that we can get those questions answered. Thank you very much for attending, and I hope you have a safe and healthy 2016. Take care.